set of values for x for which the series converges takes the form of an interval centered not at 0 but centered where? Okay, so that's very easy to show. All right. So here's an example. This one is a power series centered at 3. So how do I deal with that? So by now I have already shown you several times the trick that you usually use to use the ratio test, right? At least for most of the cases, simpler cases like this. So you look at number 5, and imagine what happens if you go from that term, the nth term, to the next one, which is the n plus 1 term. What happened to the numerator? You throw in an extra factor of what? X minus 3, right? So I have x minus 3. Another thing that you have to make sure is to do a surgery, and that is because, actually there are two surgeries that you have to do. Because you look at the denominator is 2 to the nth power, correct, times n. Now that 2 to the nth power is going to become 2 to the n plus 1 power, which means an extra factor of what? 2 in the denominator. So that means that you have to multiply a 2 in the denominator. And then the other part of the denominator is a factor of n, and that n is going to be turned into n plus 1. So that means that it's going to be replaced by n plus 1. So you have to do a surgery. You first get rid of that n. How? Multiplying. Is that right? Multiplying. And then divide by n plus 1. And now I'll manage to get rid of n and replace by n plus 1. And remember, I'm actually talking about the absolute value. And therefore I have to impose the absolute value here. So it's of this structure. Okay? And then you take the limits. N goes to infinity. What do you get? X minus 3 absolute value over 2. Right? Okay? Now its matter is clear. This is my L. So if this L, x minus 3 over 2, is less than 1, then what? Converges. If x minus 3 over 2 is greater than 1, the absolute value greater than 1, then what? Diverges. Now, this one means x minus 3. This one means, i.e., x minus 3 absolute value is less than 2. Whereas this statement here, this condition here, i.e., x minus 3 is what? Greater than 2. Is that right? So if your distance away from 3 is less than 2, then you are safe. If distance away from 3 is greater than 2, then it diverges. So the matter is very clear now. So again, here, then I say that it is, the picture is this. Here is 3, so I'm talking about number 5. 3 is here, okay? And if you are 2 units to the right, make a mark. That's 3 plus 2, that's 5. 2 units to the left, that's 1. So you're saying that if you are here, then it converges. But outside, if it is farther away, strictly greater than 2, unit 2 away from the center, then it diverges. And therefore, I know that the interval convergence must be somewhere from 1 to 5. I'm just not sure about whether it is open, open, close, close, or what, right? But anyway, at least I know that the radius of convergence is 2. So let's work out the endpoints. If I plug in 5, what happens? 5 minus 3 is 2. So 2 to the nth power, that cancels out 2 to the nth power. So really I'm talking about what? Numerically 1 over n. Right? That numerical series, summation 1 of n, diverges. So it doesn't work. All right? How about negative 1? Not negative 1. How about 1? If you plug in 1, 1 minus 3, that is negative 2, right? Raised to the nth power, the absolute value part cancel out 2 to the nth power, but you have alternating sign. So it's an alternating harmonic series. Converges. Alternating harmonic series converges. So that's the interval convergence. Let's try this one. So let me go back here again, and then use that line of reasoning. And when I use racial test to deal with this, imagine that I have a numerical value of x for x, right? So x stands for a certain number, and then so I have a numerical series, and then I'm wondering whether it converges. Then what do I do? I use racial test in going from that term to the next one. The numerator will have an extra factor of 2x minus 5. Is that right? So I'm imposing absolute value. So absolute value of 2x minus 5. That's one thing. Another thing that happens is that the denominator n now becomes n plus 1. So I have to make a surgery. I have to remove the n and replace by n plus 1. How do I remove n? Multiply by n. And then divide by n plus 1. So that denominator n plus 1. So what's the limit of this guy? Isn't that just 2x minus 5 absolute value? Is that right? Okay? X is a certain number. It's not changing with n. And therefore, if 2x minus 5 absolute value is less than 1, then what? Converges. As a matter of fact, when I say converges here, in all these cases, I actually meant what? Absolutely convergent, because I'm using racial test. Right? So if you use racial tests, then if L is less than 1, then it's actually absolutely convergent. And that's why, in all these examples, as a matter of fact, in all power series, as it turns out, it has to be convergent on the open interval part. If 2x minus 5 absolute value is greater than 1, then diverges. Okay, now this inequality here, let me rephrase it. Isn't that the same as x minus 5 half is less than 1 half? Is that right? Divide both sides by 2. Something worth knowing is that if you have absolute value of A over absolute value of B, that is the same as absolute value of A over B. Alright? Quotient of the absolute value is the absolute value of quotient. So therefore, if you divide both sides by 2, then on the left you have absolute value of 2x minus 5 over 2. But 2 is the absolute value of 2. Is that right? Okay? And then the quotient of the absolute value is the absolute value of quotient. So in other words, the absolute value of 2x minus 5 over 2. And then 2x minus 5 divided by 2, that's x minus 5 half. So we get this. And then, likewise, this inequality can be rephrased as x minus 5 half is greater than 1 half. And therefore, I know that the radius of convergence is what? 1 half. The interval centers where? 5 halves. So the picture is that I have 5 halves here. Okay? And if my distance away from it is less than 1 half, then I'm fine. If it's greater than 1 half, then it diverges. So what is 1 half to the right of 5 halves? Isn't that 6 halves, which is 3? And 1 unit, and then this one must be 2 then. So the interval must be what? 2 to 3. Okay, and then we'll investigate the endpoint later. But at least I know the radius convergence is 1 half. The interval is centered at 5 half, which is 2.5. Okay, when you have 3, tet 3, what happens? 3 plug it in. 2 times 3 is 6 minus 5 is 1. So 1 to the nth power is 1. 1 over n, harmonic series, what? Diverges. How about left end, 2? You plug in 2 times 2 is 4. 4 minus 5 is negative 1. So you have a -1 to the nth power alternating sign over n. That's alternating harmonic series. Good or bad?
Convergence.
Good. That's convergent. So it's half closed, half open. Left closed, right open. Get the idea? So this is, power series. Remember, power series, even though the book doesn't mention it, but today I make a point in preparation of the thing to come very soon. I urge you to keep this in mind. That is that even though we spend a lot of time talking about convergence issues, but the power series can be dealt with algebraically. Even when it diverges, you can still deal with algebraically. And then as you do so, keep in mind that power series resemble polynomials. And then if you have a habit of writing polynomial in ascending form, then things become very similar, especially when it comes to multiplication, for example. It behaves exactly the same way. And then you can infer that, well, when it comes to power series, obviously I can do multiplication. As it turns out, we can do other things as well. If you have, you have to put certain constraints. For example, if you want to do long division, then you have to ensure that the divisor is the one that does have a non-zero constant term. It starts with a constant term. Otherwise, it's possible to do the long division. All right, something like that. But